signature of the system that we are testing. The other ability that we have with DFR is that we don't look only at the solid insulation, but we also look into the liquid insulation and the conductivity of the system to look how contaminated or not contaminated the liquid insulation is in the system. Talking about this ITC, because it's important for you to understand the individual temperature correction, I'm just giving here an example of a system where we have the same paper sample, this is craft paper, with less than 0.5% moisture concentration. And it was tested in a wide spectrum of frequencies, right, from 10 to the minus 3 hertz all the way up to 1 kilohertz, right? So from 1 millihertz to 1 kilohertz. And it's the same sample going from 20 degrees C to 40 degrees C to 60 C to 80 degrees C. As you can see here, when we look at the 60 hertz or 50 hertz, the line frequency value, my 20 degrees C has a value, if you can see it right here, which is higher than the 40 degrees C, and it's about the same value as my 60 degrees C. And it's much lower than the 80 degrees C curve, okay, right here. So where is this value coming from at 80 degrees C? This value that we see at 60 hertz at 80 degrees C is the same value that we can see at about 0.9 hertz at 60 degrees C, is the same value that has been shifted from about 1.2, 1.3 hertz, right, at 40 degrees C, and it's the same value that we had at about 0.12 hertz at 20 degrees C. So basically what is happening is with temperature, the dielectric response is shifting, right? So to higher frequencies at higher temperatures and vice versa, going to lower temperatures. So based on this principle, we can go now and let's start looking into the factory dry out directly. When you look into the factory dry out, you may get into a very complex situation, which is a vapor phase dry out. But especially for distribution type transformers, I would say up to 50 MVA, some of them, you can get into a process that is basically thermal and later a vacuum process, or thermal and vacuum at the same time. In the vapor phase process, you have you involve a very volatile material, which is kerosene, right? So that is a different topic. If somebody has that kind of situation, I would appreciate to have maybe an email and we can talk offline about it a little bit more in detail. But the most typical here is thermal and vacuum. So let's look into these two processes, because for thermal and vacuum, when you try to do this work, and we're going to explain this through an experimental unit. When we started with this unit, we draw a benchmark and we tested the unit, just the coil and core assembly, which is just the active part of the transformer. And we determined with DFR that before the dry out, after manufacturing of the core coil assembly, we got about 4.5% moisture in the solid insulation. And this is the dielectric response that we got out of it. When we start the process in the oven, we started with a thermal process. You can see now that there's a couple of things interesting to look at. On the first side of the slide, right here, you can see the thermal profile inside the oven. And most of the time, people look at the temperature gauges from the oven, but there is a gradient. There's a thermal difference between what you see on the sensor of the oven and what you really have on the insulation system. So it's better, of course, to put probably a thermal probe directly to the solid insulation and do the monitoring. That's the way that we run this test with the thermocouple. And you can see what is the thermal profile. So this is the temperature, where you can look at the temperature profile during the process, right? And you can see, in this case, this is the not corrected 60 hertz percentage dissipation factor. You can see at the beginning, it tries to reach thermal stability, and it will go up till it gets to about this point, and then it starts decreasing the losses going down here. But it's better probably to analyze at a lower frequency that is more sensitive than line frequency. And all this investigation, and remember that when you're running in factory this thermal process, the temperature is it's about 100 degrees C. The process runs at about 100 degrees C. So it's better to look at a lower frequency, which is more sensitive to temperature variation. And that's the reason why we prefer to run the test at about 10 Hertz. But many people in history has been monitored the power factor value and its changes, but has never properly corrected it. And you can get into confusion, right, on the assessment of this power factor value if there's no proper correction. And that's the reason why ITC is being used in our dielectric frequency response monitoring. But nowadays, you can look into the thermal profile, of course. You can look into the dissipation factor changes through time. And you can also look into the moisture content. So that is the interesting thing now, that you can decide, okay, how far do I need to go in my thermal process? And most of the time for a factory, for the manufacturer, you really need to build an optimization algorithm where the temperature is one variable, then the time is your second variable, right? And of course, moisture concentration is your third variable. You don't want to overheat your insulation because you will lose degree of polymerization. You don't want to spend too much time or not enough time to dry your system. I mean, it's like cooking, right? You want to bake a cake, you don't want to overcook it, right? You don't want to burn your cake, and you don't want to bring it raw. So time is fundamental. And of course, you need to know how much moisture do you have in that system without affecting your degree of polymerization, without affecting the time that the system is working. And you don't want to overspend time because that is the efficiency of your system. If your system is dry, take it out. You need to go into a next step. And probably after the thermal process in the oven, what you will do is a vacuum process. And you can monitor the process as well during vacuum. The interesting thing here is, of course, like you can see during vacuum, at this point you don't have oil, right? It's still the core coil assembly that has been tanked. So it's inside the tank. You have sealed the cover, right? You may have dressed already with bushings or with test bushings, whatever is the case. But now in a sealed tank, you can apply some vacuum and you see how losses start going down, okay? And you can monitor this. In this example, as you can see, we went all the way to from thermal to vacuum process to filling back with oil and doing the test. And at the end, this transformer shows a dielectric response with 0.37% dissipation factor, right? Which corrected to 20 degrees C was about 0.43. And the moisture concentration at the end of the process, now filled with oil after the dry out, after the vacuum, the thermal and the vacuum, 0.7% moisture concentration. So let's look a little bit how the installation works. In the oven, of course, you put your transformer inside. If you have a vent, then you can just go from the instrument directly to the transformer with the high temperature cables. But if you're having temperature and vacuum in your oven, then you may need to go with a flange, right? And you need to put some bushings in between. We can talk in detail with anyone who needs to look into this application. But on the accessories, of course, there's a specific tool for IDAX monitoring, right? You need to have access to this application. In addition to that, of course, because the system is going to be working at high temperature, you need high temperature leads. And you can see, for example, here hanging inside the oven, some leads. You may need this flange, right? If it is completely sealed, to go from the outside, you do a connection from the instrument to the wall of the oven, and then internally you just use the high temperature leads from the wall to the transformer. Okay, so that is basically it's very simple. You need, of course, to have some DAQ, data acquisition system, and a temperature sensor for that. That way, automatically you gather the information of the temperature, and that is automatically going to the instrument for the analysis. In the field, the situation is a little bit different. When you're working in the field, you have different methods, and you will see that there's different applications, different manufacturers with different types of rigs that will be used in the field. The most common, I would say, are, of course, the heating by frequency, right? So you can heat the core by applying a change of frequency, or you can use the most typical, I guess, is the hot oil circulation plus vacuum. That is the most common method, and its application is quite broad. If we look into this one, again, let me explain the process in an example. And typically in this process, we use what is called the cold trap, where this residual moisture, which is basically kind of a mixture of oil and water and freezing, so it's really buried, right? In this example, we're using a 500 kV transformer, 400 MVA, and the process is running at about 65 degrees C. When you are under vacuum in this process, we suggest not to use high energy signal. So the signal that is being used in this case is only 30 volts AC for the instrument. It's a fast testing process. It takes about only 5 minutes, right? It will do the moisture estimation with or without oil, right? And it's of course sensitive to the effect of temperature. So we will talk about temperature a little bit more. What is the example here? What was the problem for our customer? Basically, they were used to this cold trap, but according to their standards or to their regulations and best practices, they had to reach about 4 ounces per hour, right, moisture in the cold trap to determine that the process has been completed. And as you can see, it's a very variable process, and it goes up and down, up and down. It looks like it's getting already to 4, and then it goes up and then it goes down. So it was not really stable. So the question was, should I stop the process? Is it good enough? What can I do? And the request was, okay, let's run a DFR test, right, while you are working on the unit. And this is the example. So we started with one sample, and 12 hours later, I requested a second sample. What you can see clearly here is that at higher frequencies in the dielectric response, there's almost no change. And you may not distinguish any change in your power factor or your time delta dissipation factor, right, when you're looking at the line frequency value. The ability of using DFR allows me to say, no, there is some work being done. So let's look into the process. I was able to estimate what was the percentage moisture at that time, and the recommendation was to run for another 24 hours the system. You can see that the system is working, that the losses are decreasing. So if you have all the equipment there, all the people to do the work, and the opportunity to dry your transformer, go ahead, keep going it. When you see that there's no changes on the dielectric response, then you just stop, because your system, your process is not efficient. You're just wasting time, not getting any result. And that's the beauty that you can just visualize with the dielectric frequency response. At the end, in this transformer, we were able to see the unit filled back with oil. So after all the dry out process, the unit was refilled with the dielectric oil. And you can see a very low dissipation factor, 0.27%, moisture concentration 1%, and dissipation factor on the oil was 0.02. You can understand how difficult it is to do the dry out in the field. It's not a condition like in factory. In factory, you have all the conditions for a perfect dry out. So that's your best opportunity to get a dry unit. And make sure that when you buy a unit, you test your unit for moisture with the electric frequency response, so you can be sure about the condition before the service life starts on your transformer. And with this method, throughout the time of service, after 10 years, after 15 years, when you're doing a dry out on your transformers, please make sure that your transformer is going down on the moisture. That if you have, for example, something 230 kV and above, the idea is to go below 1% after a dry out, okay? So just as a reference. So the dry out process in the field requires some temperature monitoring. Like we were explaining in the process that we have for for the factory, we use only a thermocouple that we put next to the coil or next to the solid insulation of the transformer, and we keep monitoring from the sensor directly the information. But we cannot do that in a field dryout process. So the easiest way and the most certain way to do the temperature measurement is using winding resistance measurement, okay? But you need to have a reference. Based on this, you don't get into inaccurate assessment of the moisture, because I have seen many people looking just at the temperature gauges on your transformer, and that is not correct, because now that you don't have oil in your transformer, that you have drained the oil, the thermal well where the PT100, where the temperatures probe resides, is not doing the work, and there's a big thermal difference between the thermal well and the insulation that you might be showering with hot oil. So you have to be careful about that. And the best way, because the distribution of the solid insulation is along the windings, the best way, of course, is to do a winding resistance measurement. And don't use more than 1 amp. Go on the high voltage side where you need the lowest current, of course. And your typical winding resistance piece of equipment does not exceed 30 volt or 50 volt compliance voltage. So you are in a range that is not a risk to do this test during vacuum. Okay, so one of the things important for you to know is when we do DFR on a transformer and you are doing a thermal vacuum process in the field, you do not need to break vacuum. Okay, the only thing that is suggested is to stop the vacuum pumps. Don't break the vacuum, right? Just stop the vacuum pumps so you don't have any dynamic process during the measurement time. And it's only for 5 minutes. So typically you have cycles, right? You have cycles of 6 hours or 10 hours, depending the equipment that you are using in the field for the dry out. Give the guys a smoke break, right? Or a little break for coffee. And you run your test on dielectric frequency response for about 5 minutes, 5 to 10 minutes, depending on the temperature. And that's all you need. So with that being said, when you look into this temperature monitoring, right, our equipment is capable to look into the resistance, and based on the application of formulas that are well described in the standards, I can convert the resistance value into a temperature value. But it is good for you if you're doing this from factory. Of course, you can have your heat run test, right, and you have the information about winding resistance correlated directly to your temperature values of the winding. And if not, when you are commissioning your transformer, make sure that you do your winding resistance properly, that you have a good reference of the temperature, because that will be a reference for the future to do this analysis, okay? And of course, you can clearly see here the changes in temperature and the resistance. You can get a chart for that. This is the typical chart that we use for heat run test, okay? And we do just by changing the load on the transformer, and we measure the winding resistance, we can see the temperature. That's basically what happens in this process. So a little bit of conclusions about the factory dryout process. Continuous monitoring using DFR allows you for a faster response. It's a better moisture assessment. You can directly analyze the condition of your transformer. It's less time, less manpower required for dryout. And again, you can run, you know, for you who like to run some mathematics and some optimization algorithms, as I said, just think about time, temperature, and moisture concentration, and make sure that the work that we do, the work that you do, is to provide to your customer with the best possible unit. So he's going to be happy with that transformer. He's not going to have any issues with the transformer. He can load the transformer during an emergency, overload if necessary, right, for short periods of time, and he is confident that the transformer will work well and he's not going to go into a potential failure. Less energy required, of course, is savings. It works with thermal and vacuum process dry out, so it's universal. And of course, it's much less time and guessing versus dew point or Carfisher titration. So it's a direct method that you will analyze the moisture concentration through the dielectric response of that specimen that you're testing. In the field, of course, remember that for your DFR dry out, it will be in cycles every 6 hours probably. It's an average of time that you need when the first heating the core and coil assembly with hot oil. You spray the hot oil on the core coil assembly internally, and it hits the coil, and you start your process, you start vacuuming, you start extracting your moisture, and then you need to, again, crank up some temperature. So you go and you spray again some hot oil on the system, and in that period of time, just stop the pumps, don't break the vacuum, measure the resistance of the coil, get the temperature, and do your assessment with DFR technology. So it's very simple. And the beauty, of course, here is that you will have an ideal feedback of the condition and the process. Where are you? Can you finish? It's enough. Are there any changes on the dielectric response or not? You can see, of course, also the features of ITC, and of course that is going to help you a lot in the analysis, looking into the dielectric response and how it changes with the effect of temperature. You have control on the process. You can control and you can be much more efficient on the way that you're running your dry out process in the field, basically. So let me show you quickly how the factory dry out process and the field dry out process is monitored and is taken care in the field and in the factory with IDAX monitoring. So let's start here. How do you set up IDAX monitoring? As you can see, first, this is the IDAX screen, the software. When you look into the settings, if you click on the settings, you will see here all the specifications that you need. And at the bottom, you see where it says active monitoring. So this active monitoring is basically the application that will allow you to run this monitoring system. You need to register and you will receive a license number. I'm not going to share my license number here, but you can see now that the monitoring has been enabled. Once it's enabled, you can look into different tables and references and other features that will allow you to set up your system. If you're doing a transformer, you will select the T1 2020 model, right? You can look into the different settings that we have provided for in a traffic light system, what is good, what is bad. The sleep time, so how often do you want to run the test? Typically, in the factory, I would suggest a 30-minute to a 60-minute sleep time. So in intervals of about an hour to do the measurement. That is more than good enough to know exactly where you are. So when you create a new file, you can clearly see that you can select a moisture test, you can do your ITC test, just a DFR, your dissipation factor, you can do a DC test with IDAX, or you can set up for a monitoring system on the last icon that we selected. You select the object, in this case a 2-winding transformer, you can provide the name of this, whichever way you want, so you say dry out. It is very important to provide the temperature. Ambient temperature is just for reference. It will not influence the measurement and the application of ITC, but the object temperature is fundamental. So from here, you will see if you have some mineral oil. If there is no oil, then you just change that and you select that you're with air surrounding the system. And you can see now that we have a different screen. On the right-hand side, the settings, you see that the voltage that we have selected here can go up to 140 volts RMS, but typically we set something like 50 or 30 volts. In this process, in this example that I have selected for you, you can see the temperature, right? So there's a plot of the temperature. You can select the source using a DAQ, as I was explaining to you, so you can use just the sensor and acquire the information for temperature directly into your system. So the information about moisture goes together with the information about the temperature, right? So you have the date and the time for the information. You can load an external file if you have used an external file for that. Now you can look at the sweeps, and you can look, like you can see at the bottom here, you can look into the capacitance, you can look into dissipation factor or power factor. and select any of the measurements that you have done during the time of test. So I can select, for example, capacitance and dissipation factor, and you can see the change of those curves. From the very first curve, right, the very first dielectric response that I got at the beginning of my process, you can actually do a training of the changes on this dielectric response as moisture is extracted from the solid insulation. It's also, of course, the influence of the temperature. So there might be a little bit of increase in your dissipation factor because the solid insulation is reaching some thermal equilibrium inside the oven, right, with respect to the temperature of the oven. And then you will just keep tracking. You can look into the capacitance, or you can look into the dissipation factor, and you will see how losses are going down, and the capacitive response, right, the capacitance as a function of frequency, this is getting smooth, and it's lowering this kind of exponential curve that you can see in this case, okay? And you can look at all the responses here. You can see exactly the changes. So it's very simple for the practical eye to look at this dielectric response and know where you are in the process, okay? And then finally, you can select just the characteristics that you want to monitor. In this case, you look at the thermal profile, which is the upper line. Then you have the dissipation factor, and finally, you look at the moisture concentration in the insulation, which is the black curve. So you can look into all these characteristics, and one of the things that I like to look is also at the stability on your dissipation factor, stability on your capacitive curve. When you are in the field, basically you do a moisture analysis, okay? So you select a new file, you select the moisture, you select the type of transformer that you have for the test. It could be a 2-winding transformer, it could be a 3-winding transformer. You will label it. And again, you need to provide information about the ambient temperature and the object temperature. With that information, that is the reference for the analysis, and make sure that you have a good temperature value. If you don't use like winding resistance method to determine the temperature when there's no oil in your transformer, then the analysis will be difficult for interpretation. And you can see here, depending on the temperature, we have the stop frequency. Normally you will go down to 5 millihertz when you're running hot in your transformer, about 60 degrees C. If it is 30 degrees C, maybe you need to go down to 2 millihertz. The voltage, again, you can change the voltage. If you need to go down, you can go to values like 50 volts, 40 volt, 30 volt, whatever is required. And then you repeat the test in cycles, right? When the processing cycle stops and you need to heat again the coil course assembly, that is the opportunity that you have to run the test again. And you will go and you will look into the different into the changes of the dielectric response in time, and you can see how the changes are being monitored, and you have the analysis of results. If you look under the curve, you see that moisture has gone from about 3% at the beginning of the process and all the way down to about 2.2% in this case. So with all that information, you can look, you can analyze the system, right? One interesting thing here is I normally suggest to look into the characteristics, capacitance, dissipation factor. When you compare power factor and dissipation factor, here's the part that I'm a little bit concerned, especially when you have high losses. Power factor cannot go beyond 100%. But dissipation factor, the limit is infinity. So I can clearly see the changes, right? Especially on the very low frequencies with dissipation factor. And that is my preference when I'm looking into dielectric response and when I'm looking into the monitoring process in the field. I will look as well into my capacitive changes, how the curve is being changed during the process. I would expect a final linear response of my capacitance at the end of the process. That would be the ideal condition. So That was a very quick introduction for you on the IDAX monitoring software and the way that the test is carried out in the field, the process. As you can see, there's no complexity. It's a very simple process. And with that being said, I will give the mic now to Mr. Michael Evangelista to talk a little bit about IDAX 300. Michael?
Yes, thank you, Diego. So in the slide that is shown here is our equipment for DFR. That is the IDAX 300. We have two models there. As you can see in the picture, we have the IDAX 300, and the one below is the IDAX 350, the one with the onboard computer. So this IDAX is made for the state-of-the-art measurement of moisture content, tan delta and power factor, and also oil conductivity using the DFR technology. So this DFR technology used by IDAC has been continuously developed and updated for more than 20 years now. As you may know, the first portable DFR device in 1997 was delivered by our very own Dr. Peter Wirelus, who is in Megger, Sweden. So meaning Megger has mastered this DFR technology through its wide and many years of experience. So this IDAX has an easy-to-use software with automated measurement, flow, and analysis of test results. So we have this traffic light principle for easy interpretation, and it is made for the convenience of the user. It also have dedicated test procedures for power transformer, bushing, and current transformers. So meaning the user may be guided with the connection as they may refer to the illustration or the diagram that you have seen in the slides of Diego. So that can be found in the software. So for me, I personally like this feature as this will help the user as they don't have to spend more time in learning the use of the equipment. Another unique feature that is also discussed by Diego a while ago is the automated individual temperature correction for accurate comparison with reference data test. So this feature will give you more accurate way or alternative way to do the temperature correction on your tan delta testing, for example, as it will give you more information of the actual condition of your transformer before doing the temperature correction. And furthermore, as far as I know, this is the only equipment available in the market with optional amplifier to inject up to 2 kb for reliable measurement, even in a high interference environment. So it has interface to high voltage amplifier. So next slide, please. And for more information, you may check out the Transformer magazine. There was an article there, or an article written by our presenter today, Dr. Diego Robalino, which is entitled "The Factory and Field Dry-Out Power and Distribution Transformer Monitoring Process Using the Dielectric Frequency Response." So for our next webinar schedule, you can see in the screen. On August 10, we have the cable fault location, which will be done by somebody from the factory on August 10, 4 p.m. Hong Kong time. We have the condition monitoring of electrical motors on August 11, 10 a.m. Hong Kong time. And we have the industrial electrical testing, test or brand and IR testing on August 12. And we have the basic of distance protection on August 13. So I guess that's the end of the presentation. And for those of you who have questions, you can send us also email through these contact details as you can see in the screen. And you can still type in your questions in the chat box if you have questions, and our panelists will answer those questions. And by the way, for those who are leaving this webinar, please don't forget to fill up the survey, because that survey will really help us in improving our future webinars. So again, thank you so much for attending this webinar. Now let's move on to the question and answer portion. And we have some questions here for Diego. Can we monitor the dry-out process for bushing and CT? Diego?
Yes, sir. Thank you very much for the question. That is actually a, a new application that we have been working for quite some time. Actually, I truly invite all the attendees to look into some of the publications that we have. And one of the things that I want to highlight here is we as Megger, we have many technical resources, and there's lots of research work that we have done, and we have a big data information database that collects, especially on the DFR side. We've been doing this for more than 20 years, so you can imagine how many files we have collected on this. For bushings and CTs, actually, it brings me back to my years going to school and getting my PhD in electrical engineering, because my work was focused on medium voltage and high voltage oil impregnated paper CTs. And the answer is yes. Actually, after the last, I would say that for the last 10 years, we've been working with different manufacturers on the dry out process for bushings and CTs. It's not as easy as it is for transformers. There's some complexity here. And if you have some specific question and you would like to talk to us, we will need to visit your factory, visit your site, and take a look exactly at what is your setup. But that is doable. Actually, some of the papers, if somebody is interested, of course, please send us an email, and maybe we can share some of the information that we publish on some of the thermal analysis, for example, with DFR on high voltage bushings. And high voltage bushings is a hot topic right now. And we have done quite interesting work on the analysis of the condition of bushings, because even today, with the latest publication from SIGRE 755, and I know that maybe Ankit can talk a little bit more as well on that area, there's certain parameters that are not as easy to understand, right? And I think it's part of our responsibility with the community, with the technical community, to clarify some of the limits that we can provide on bushings and CTs. As I said, for dry out, the answer is yes. It's a little bit more complicated, the process, right? But it's a very interesting case, because when you do the dry out for bushings or CTs, you put like 20, 30 units inside the oven, right? But you go in a range from, I don't know, 123 kV all the way up to 800 kV. And you can have a variety of sizes, a variety of insulation systems. So it's very important. It's very important for manufacturers to keep a very efficient process and make sure that your product, I mean, you don't need to dry out a 200 kV bushing the same way that you need to dry out a 500 kV bushing. So it's a question of temperature, time, and moisture concentration. Let's go to the next question.
Okay, thank you, sir. So the next question here is, can IDAX 300 be used for periodic maintenance, example, 6 months, etc.? I can answer this one, sir. Sure, sir. So the more tests you are doing with your transformer or in a regular basis, the better. Because you know why? You are checking continuously the condition of your electrical system or your transformer. However, of course, since this test is being done offline, so you need some downtime. You need to shut down your transformer, and that implicates cost, of course. Okay. And since you are doing, or you will be using IDAX 300, IDAX 300 can also do insulation power factor test, and you will have different results when you do regular testing. So you have this trending, you have historical data, and that will lead you to predictive maintenance. So at least when you do this predictive maintenance, then you can at least, foresee or looking ahead when will be the next maintenance schedule for your transformer, for example. So maybe Diego can also add onto this.
Yeah, what you said is exactly right. I mean, if you are doing a power factor test, right? And if you have not done before a dielectric frequency response test, I would strongly recommend you guys to use the time when you have your testing available, because the different utilities may have different opportunities for a dielectric frequency response test. Somebody may have every 2 years the opportunity to do a test. Somebody may have. I remember going to a utility and they disconnected the transformer after 8 years, that they were not able to take out of service that unit, right? Because it was a kind of a critical unit for quite some time. So whenever you have the opportunity to do your typical routine testing on your transformers, and if you have not done this before, I strongly suggest to incorporate DFR. And remember something else. The DFR now has a reference with IEEE. Most of you follow IEEE, most of you follow IEC or C-grade documentation, but the IEEE document C57161 is the DFR guide for transformer testing. So just keep that in mind.
Okay, for the next questions here, IEEE or IEC correction tables also applicable to correct the tan delta value of reference temperature 20 degrees. Then why ITC? Ankit, can you answer this one?
Yeah, I would like to answer this question. See, earlier what we used to do, because we know that the tan delta is strongly temperature dependent, so ideally the utility which they used to convert the ambient temperature tan delta value to down to the reference temperature 20 degree. And earlier what they used to do is, or some of the utilities still doing that, they are using the IEEE and the IEC correction factors. So as per the recent amendment of IEEE PC 57.12.90 saying that the experience has shown that the variation in the dissipation factor or tan delta with temperature and substantial and erratic, so that no single correction curve will fit in all cases, because we know that the every transformer has got different temperature dependency. So this single correction curve will not fit in all the cases. So that's why in the Diago presentation you can see that the unique technique which has been introduced by, which is known as the individual temperature correction factor, which is based on the variable frequency tan delta technique, which can be utilized in order to estimate the actual temperature dependency of the transformer. And you can calculate, I mean, the software will calculate automatically the actual temperature dependency, and you can generate the actual temperature correction factor. So, okay. Diego, you want to add something? Yeah.
No, you're absolutely right, and I like very much your comment, because IEEE C5712, right, had a statement up to 2006, and that statement was removed with that correction that you just mentioned. So, and like you saw on the software that I was showing you, the changes on the dielectric response, when you change the moisture concentration, where you're doing a dry out, your dielectric response changes. So if your dielectric response has changed, then you cannot apply the same correction table just by the nameplate. You may have similar transformers operating in different places, but the loading, the potential of a fault in the system, different conditions, moisture, contamination, I mean, they are not equal one to the other. And having the unique dielectric signature, which is your dielectric response, allows us to go into this ITC, or individual temperature correction algorithm, which is the reality of the temperature or of the thermal behavior of the dielectric response. So very well responded, Ankit. Thank you.
Yep, thank you, sir. Next question for Diego. 1 Hz tan delta is very sensitive, so I can monitor the drying process using Delta 4000?
Interesting question. Interesting question. You can, again, you can monitor and you can run what we call the narrow band dielectric response, okay? With the delta, and the narrow band will allow you to go between 1 Hertz and 500 Hertz, right, with the delta unit. But for factory monitoring, I would suggest to go with a wider frequency band, with a wider frequency spectrum. We need to be within the range of temperatures, and that shifting because of the thermal behavior may not be sufficient with 1 hertz. Okay, so the ideal tool for monitoring, right, which includes the software and everything, you can train 1 hertz, right, but the idea is to be able to monitor from 1 hertz to what the moisture concentration is, and for that all the tools are with the DFR full unit, which is the IDEX. Okay.
Okay, thank you, sir. So another question for Ankit. We are manufacturing 150 kV DC source for ESP application. What will be clearance between high voltage and earth for DC application?
Yeah. So exactly, I cannot remember what is the exact number, but I can refer it when it comes to 220 kV station for the DC clearance is required 4,500 mm. So this is, I mean, one of the document is saying that 4,000 mm, 4,500 mm is required for the clearance for the 220 kV system from ground to earth.
Okay, thank you so much, Ankit. I guess this is the last questions that we have for Diego. How long it is safe to test continuously using IDAX kit for moisture content during typical dry out process in the field, if it is intended to do so, safe in view of the kit?
The test is low voltage, low energy, so the unit can operate as long as you need. Typically, again, it's all related to temperature. So if you're doing a field test and we're talking about a monitoring process, as I said, in the field, you will do this in cycles, right? After 6 hours, when you are you're basically spraying hot oil again to the coil core assembly. And the test will last for only 10 minutes, 15 minutes. So that makes no difference. It has no effect really on the unit or on the transformer. So everybody is safe. That is not a limitation at all. Actually, one thing that I would like to, in the next, I think we have a couple of minutes more, I would like Ankit also to talk a little bit about bushings, because there's a very interesting question on the beginning about bushings and CTs. And one of the challenges actually is to do the DFR on the bushing in the field. And that is because of extra high voltage substations, especially in Asia. You guys are the most knowledgeable on extra high voltage systems with voltages in the 750 kV and higher, and there's lots of noise. So if Ankit, could you please make a quick comment about the high voltage DFR application on bushings?
Yeah. When we are talking about the DFR test on the bushing, so as per our experience when we are working in one of the 765 kV station, and that there was a very interesting thing when we have the bushing, which is the capacitance was in order of, let's say, 750 picofarad. And when we are going towards the lower frequency, we experience the negative tan delta value. So we tried to find out this particular issue, and so we find out this particular issue. This is because of the low capacitance object, and where you have noise as well as due to the low capacitance object, the magnitude of the current is also low. So the instrument have very hard time to measure that at lower frequency. So to address this particular issue, what we have done, we have increased the voltage 10 times. Let's say IDEX 300 was using 140 volt, and then we increase the voltage to 1400 volt RMS, or you can say 2 kVp. And with that particular voltage response, my curve was very flat, and we get very clean measurement, especially on the low capacitance object. So we recommend to our customers also, when you are testing the bushing and the CT, especially the low capacitance object, please use IDEX 300 plus VAX 2 kV amplifier, which will give you the complete, clean, reliable measurement in the high noise stations. Yeah.
Thank you, Ankit. That is a very important comment, because some of the, especially the big utilities working on extra high voltage systems, we'll face the issue of having a low capacitance object, right, with a high noise, surrounding the testing area, right? We cannot cancel the noise, so the only thing that we can do basically is to play with signal to noise ratio. We have more questions, Michael?
So we have another question here, sir. During construction and installation for new transformer, what method is used to check the condition of the transformer? It is perfect for startup and commissioning. Do you want to answer that one, sir?
Okay, so think about this. You should have a commissioning process, right, before any startup. And you need to make sure that you look into every corner of the construction of your transformer. You need to make sure that the dielectric construction is in perfect condition. You need to make sure that the mechanical construction is in perfect condition. You need to make sure that the electrical construction is in perfect condition. So, and the thermal as well. So thermal, dielectric, mechanical, and electromagnetic, I would say. Okay? So with that in mind, you have different components as well in your transformer. For example, you can say, I want to look into the windings. Okay, windings is one part. So you can do your winding resistance, you can do your ratio test, you can do excitation current. But you have a tap changer. Okay, so what kind of tap changer do you have? Do you have a resistive type? Do you have a reactive type? Do we need to do some additional analysis? Can we go into getting a signature of your electromechanical system with the SFRA? So sweep frequency response analysis, for example, is one of the advanced methods, and it's extremely useful to understand and to create actually a benchmark of the condition, of the electromechanical condition on your transformer. Then if you look into dielectric system, your basic system, of course, you start with a dissipation factor tan delta test. And I would strongly suggest for the beginning service life of your transformer to have a full dielectric response of your system, right? If you can get that as well from factory. So you make sure that the bulk insulation is dry. If you have a transformer that is 230 kV plus, you will look for 0.5, 0.6% moisture at the beginning of the service life, okay? And then, of course, look into all the components that you have. You have bushings. You need to make sure that you do your dielectric test, you do your integrity test. As soon as you energize your system, make sure that you do a thermal scanning on your transformer so you can see that everything is working fine, that you don't have any hot spots on connections or anything like that. So there's a whole procedure. I think that if somebody has some specific questions about, there's recommended practices for the factory for testing and factory acceptance testing, and there's recommended practices for the field. So we can talk about both, but most important for you is to make sure that you have looked into the thermal, dielectric, electromagnetic, and mechanical aspects of your transformer before you energize it.
Very well said, sir. Thank you so much for the answer. So I guess that's all the questions that we have for today. And for those of you who have any more questions, you can send us an email in the email address you can see on the screen right now. So again, thank you so much everyone for attending this webinar, and especially we thank Dr. Diego Robalino for your time, sir, here in Asia. Thank you so much. And also thank you, Ankit, for attending this webinar as a panelist. So again, everyone, thank you so much for attending this webinar. Have a good day and please stay safe. Thank you so much.
Yeah, thank you, everyone. Good day.
Thank you very much. Thank you very much. Stay safe.
Thank you. Thank everyone. Thank you.